Hi everyone, I'm Professor McBain. Welcome back to Chem 100 and welcome to our lecture series on what is science. All right, let's start talking about what is science and what isn't science, what isn't scientific. So Dr. Sheldon Gottlieb said in a lecture series at the University of South Alabama that science is an intellectual activity carried out by humans that's designed to discover information about the natural world in which humans live. And one of the big important things with science is that not only do we just discover information, but we also try to put that information into meaningful patterns, right? It's one thing to memorize a bunch of facts, but you should also be looking for some overarching principles about how things go in your discipline. And so again, a primary aim is to collect those facts, but an ultimate purpose is to discern the order that exists between and amongst the various facts, right? You might remember the scientific method from elementary school, and it was a little complex, right? Sometimes, depending on your school, you learned about, you need some background information, and then you establish a hypothesis and this and that. Here's the scientific method in the most simplified manner that we can explain. All right, so first you look around the world and you find something of interest and you collect some information about it. Then step two is that you form a hypothesis about why things are happening in this way. And then that hypothesis needs to be able to be tested. Okay, so you have to come up with a way to confirm or refute whether your idea is reasonable or not. Okay, and so then once you've got results, then you either say, yep, I was right, or nope, I'm totally wrong, or wow, these results didn't tell me whether I'm right or wrong, and maybe I should modify what my hypothesis is. And so then that modification would theoretically lead to gathering more data, and then you would perform more tests and so on, and you might even just gradually modify your hypothesis until you get as close to the truth as possible. So there are a lot of examples of the scientific method having been in action in the past, but one of my favorites that I like to talk about in this class is the models of the atom. Okay, so way back in BC days, Democritus came up with this idea of the atom. Then finally Dalton picked it back up in 1803. And so we had these ideas that there would be this indivisible smallest particle of matter, okay? And then in 1897, Thomson picked up Dalton's idea and started developing some more ideas of the atom. So it was just thought that this atom was just this blob of stuff. But then gradually we started to discover the presence of electrons. And so it was thought that these negative electrons were just hanging out in this big pile of positively charged stuff. This is what we called the plum pudding model. And then eventually Rutherford discovered that there's actually a lot of space in an atom, all right? But there is also a small unit of positively charged stuff. So Rutherford helped us discover that yes, there are electrons, but there's also a lot of space for stuff to pass through, but there's also a very small, solid, positively charged thing. Then Bohr helped us discover that those electrons aren't just free floating or free spinning in space, they actually have different energy levels. And then gradually all of these guys like Einstein and Schrodinger and what have you helped us discover the modern quantum mechanical cloud model. So you can see that we've had this idea about atoms for a really long time, but over time the theory itself of what an atom is and how it's structured has been developed by a lot of different people. So here are some opinions about scientists from other scientists. I think that we shall have to get accustomed to the idea that we must not look upon science as a body of knowledge, but rather as a system of hypotheses or as a system of guesses or anticipations that in principle cannot be justified, but with which we work as long as they stand up to tests. I think that that's a really great way of explaining science, you might reword this to say that scientific theories are our best current idea of the truth, or be more like the opposite of what is false. And I think that this evolution of the atomic theory demonstrates that pretty well. Another quote is that we scientists probably wouldn't know truth if it jumped up and bit us in the ass, but we're probably fairly good at recognizing what's false, and that's what science does on a day-to-day basis. But we can't claim to identify truth. I think that that makes sense. You know, just a couple seconds ago I said we're good at identifying what is not true. And so again, even though this ended up not being as close to the truth as possible, we knew at this point that there had to be some distinction between a positive charge and a negative charge at this point in the history of the atom, right? And so it would have been absurd to just say, oh no, it's still like this. Yeah, Thomson collected all this data, but it's still like this. It's crap. No, at that point we could identify that, well, there's definitely got to be some charge separation here. Even though we don't know that it's more like this cloud, we know that there's some charge separation. So I used this word just a moment ago, but we really need to define it. So what is a theory? So in normal conversational use, a theory means something like a guess or a hunch, like something that you might see on Law and Order or other, true crime types of TV shows. They have this idea, but they don't have all of the evidence yet. So in science, it's actually the opposite. When scientists say theory, a theory is a well-substantiated explanation of some aspect of the natural world, and it's got a ton of data to back it up and a ton of hypotheses that have been tested many, many, many times to back it up. So not only are there observations, but there's also a series of tests that have been performed that confirm this theory, okay? Or a more complicated way to explain that is that it's an organized system of accepted knowledge that applies in a variety of circumstances to explain a specific set of phenomena. Another way to explain what a theory is that it's a scientifically accepted general principle or a body of principles that's offered to explain natural phenomena. And this explanation is consistent with evidence, data, and experimental results. And so theories can be disproved. You can't really prove a theory to be correct. You can just kind of confirm that the theory still holds up to the data, but you can come up with a way to disprove a theory. So there have been several major scientific theories, such as Einstein's theory of relativity. There's atomic theory. There's the quantum mechanical theory. And I mean, these, I hate listing them first because most people in this course at least aren't familiar with them, but these are the ones that are most relevant to chemistry. But these, such as the theory of natural selection, aka evolution, or the germ theory of disease from biology, or plate tectonics, which we get from the geological sciences, these are ones that you're probably more familiar with, and they're all theories, okay? So let's talk about plate tectonics, right? So the Earth's crust has different plates, and earthquakes happen when those plates shift or move apart, right? And so this is, quote unquote, just a theory, but it's very well substantiated. Same thing with germ theory of disease. You catch diseases because you came into contact with someone that had that germ, and then somehow that germ passed into your body, and now you've got whatever they got. Natural selection is another one, right? We gradually evolve and so on and so forth. Even gravity is a theory, right? And so the reason why objects will fall if you let go of them is because there's a gravitational force that pulls those small objects towards the bigger one. Let's talk real quick about whether theories are facts or not. And honestly, it really depends on what point we're at in that theory's history. And at this point, evolution could be confirmed as a fact. There's a debate over definitions. In science, fact has actually two meanings. Fact means an objective and verifiable observation. But did we observe evolution ourselves? Did somebody, go back in time and take videos of these animals evolving over time? No. But fact can also mean that it's an observation or prediction or retrodiction that can be confirmed to such a degree that it would be absurd or perverse to say otherwise, okay? So back to the idea of gravity, I suppose that apples might start to rise tomorrow, but the possibility does not merit equal length of time in a discussion, right? It's absurd to propose that apples aren't gonna fall. Similarly, you can talk to the bioscientists and biologists about evolution, but there is such a broad and deep body of evidence supporting evolutionary theory these days that it would be absurd to say that we evolved from single-celled organisms in any other way, right? Or, well, there it is. I use that word in the sentence, but it would be absurd to propose that we went from being single-celled organisms, which we have a record of, to suddenly, you know, humans being here alongside dinosaurs and all of that, right? So anyway, just ponder that a lot of these theories that are popular and are well understood by the public are so well substantiated that it's kind of absurd to propose that things don't go exactly that way. Will these theories continue to be developed? Of course, just like atomic theory. In fact, there might be more developments on atomic theory in our lifetime, right? But that doesn't mean that there aren't atoms. All right, that seems like a good pausing point. Next video, we're going to be talking about the characteristics of a scientific theory so that you can spot one, but also so that you can spot something that is not a scientific theory. Find out more next time.